So we need to prove the theorem that states that if A is diagonalizable if and only if algebraic multiplicity of lambda equals the geometric multiplicity of lambda. So proving, starting with, let A is diagonalizable. That means A is similar to a diagonal matrix D. A is similar to a diagonal matrix D. Now let D equals to the diagonal. What does it now? How does we get this diagonal matrix? Just considering the eigenvalue along with the diagonals. And for a diagonal matrix, all the other elements will be 0. So it will be the diagonal of lambda 1, lambda 2, dot dot lambda n. Where what is lambda 1, lambda 2 and lambda n? These are the eigenvalue or the characteristic value of the matrix A. So D is equals to the diagonal of this quantity, this matrix, where these lambda i's are characteristic values of A for I equals to 1 to dot dot n. Okay, and as we are saying A is similar to D, A is similar to D, that means there exists, according to the definition of similar matrix, there exists a non-singular matrix P, such that P inverse equals D. We can write this, or P inverse AP, the same thing. We can write this. This should be equals to D according to the definition of similar matrix. Now what is D? D means this matrix, the diagonal elements lambda 1, lambda 2, dot dot lambda n. All the other elements are 0. Now consider lambda be an R-fold eigenvalue. Okay, we need to prove the algebraic multiplicity of lambda and the geometric multiplicity of lambda, both should be same. So let us consider, let algebraic multiplicity of lambda, any of the eigenvalue, is equals to R. Okay, that means lambda is an R-fold eigenvalue. That means in the characteristic polynomial f, lambda occurs like x minus lambda whole to the power r into some another terms, right? This one. So the algebraic multiplicity of lambda is equals to r. That means among all that n eigenvalues, lambda 1, lambda 2, dot dot lambda n, if one eigenvalue having the algebraic multiplicity r, that means exactly r of lambda I should be equal, and they are equal to lambda. Exactly r of lambda I are equal to lambda, because lambda is an R-fold eigenvalue. Then consider the matrix D minus lambda I. Okay, we are saying exactly among lambda 1, lambda 2, lambda n, r of them are equal to lambda. So whenever we are considering D minus lambda I, this r of them for their diagonal element will become 0. So D minus lambda I will become a diagonal matrix, with exactly r diagonal element is equals to 0. Because D was look like, suppose if we are choosing the first r eigenvalues are equals to lambda, so it will look like lambda up to lambda r times, then lambda r plus 1 dot dot lambda n. Now we are minus lambda I means 1, then 0, 0, 0, 0, 1, again 0, and so on. That is, only the diagonal elements are 1 and all the non-diagonal elements are 0. So if you subtract this D minus lambda I, this will become 0, 0, 0 for rth times, and there are lambda r plus 1 dot dot lambda n. So this is basically we are saying, that is D minus lambda I will be a diagonal matrix with exactly r diagonal element equal to 0. and the remaining n minus r elements are non-zero. Now for the diagonal matrix, what will be the rank for this diagonal matrix whenever we get n minus r elements, non-zero elements? So the rank of d minus lambda I, it will be n minus r, as it is a diagonal elements having the n minus r non-zero diagonal element. So we get rank of d minus lambda equals n minus r. Now again a minus lambda I, it can be written as p inverse d minus lambda I into p, because a is p inverse ap, or d is ap inverse. So a is p inverse dp. Just instead of a we are putting a minus lambda I, and instead of d we are putting d minus lambda I. That's it. Then we can get this equation. Now, and the rank of the matrix remain unaltered when multiplied by any non-singular matrix. That means we are multiplying this matrix by the non-singular matrix P and P inverse. So its rank will be unaltered. That is, its rank will be equal to the rank of d minus lambda I, which is equals to n minus r. So from here we can say the rank of a minus lambda I, which is equals to n minus r. Okay. That means what will be the rank of the characteristic subspace of A corresponding to lambda? In the next line we are writing the rank of the characteristic subspace of A corresponding to lambda is equals to n minus the rank of a minus lambda I, and we have just proved that the rank of a minus lambda I equals to n minus r. So putting it n minus r, which is equals to r. So we get that the rank of the characteristic subspace corresponding to lambda is equals to r. That means the geometric multiplicity of lambda is equals to r. So from there we get geometric multiplicity of lambda equals to r. We have started with the algebraic multiplicity equal to r, and we get that the geometric multiplicity is equals to r also. That means algebraic multiplicity and geometric multiplicity both are same for the eigenvalue or the characteristic value lambda. Now we need to prove the converse part. That means if the algebraic and geometric multiplicity are same, then the matrix will be diagonalizable. So conversely, let AM equal to GM for each eigenvalue lambda, for each eigenvalue lambda of A. Okay. Now considering mu1 comma mu2 dot dot mu s be the distinct eigenvalue of A, be the distinct eigenvalues of A. That means lambda is taking these values. Lambda denotes all the eigenvalues. Here we are considering all the distinct eigenvalues of A, mu1, mu2 dot dot mu s, and their respective multiplicity as r1, r2 dot dot rs, and their respective, these are the algebraic multiplicity. Okay, and we are considering their respective characteristic subspace according to lambda 1 associated with mu1. The characteristic subspace we denoted by w1. Then for mu2 we are taking it w2, and so on up to ws. Then according to our given condition, that is AM should be equal to GM. That means what will be the rank of this w1, w2, ws? It should be, for w1 it should be r1, for w2 it should be r2, for dot dot up to for ws it should be rs. That is rank of each wi should be equals to ri, where I runs from 1 to dot dot s, because we have taken that AM equals GM for all the eigenvalues. So then we consider the distinct eigenvalues as mu1, mu2 dot dot mu s, and their corresponding algebraic multiplicity as r1, r2 dot dot rs, and their corresponding characteristic subspace as w1 w2 dot dot ws. Then the rank of w1 w2 dot dot ws, that is the geometric multiplicity of the eigenvalues mu1 mu2 dot dot mus, should be r1 r2 dot dot rs, that is rank of wi equals ri, where I runs from 1 to s. Now we are considering a basis for each of w1 w2 wi. Let xi1 comma xi2 dot dot xi ri are the basis for wi. Obviously I runs from 1 to s. That means for w1 a basis is xi1, for w2 a basis is xi2 dot dot, for ws a basis is xis. Now we will show that these vectors, this considering all that xij vectors, this xij vector are linearly independent over K. We need to prove that this set is linearly independent. So for that reason, what we have to do, we have to consider the relation, that is C1 xi1 plus C2 xi2 dot dot CRI xiri equals to some theta. Then we need to prove all that C1 C2 and dot dot CRI should be equal to 0 for proving this is linearly independent. So starting with this condition, Cij xij, this is equals some theta. We are considering this over summation. Here are two variables, where is I runs from 1 to s and j runs from I to ri, 1 to ri. This is equals to theta. Now we need to prove all that Cij is equals to 0 to prove that xij's are linearly independent. Now we are writing this summation as, in the next line we can write it as summation over Cij xij, that was our exact summation. Now we can write it as summation over I equal to 1 to s, then Ci1 xi1 plus Ci2 xi2 plus dot dot Ciri xiri equals to theta. That means the first one we are considering it as y1 for I equal to 1. Then for I equal to 2 we will get another set of value. We are naming it as y2. Similarly up to dot dot, for I equal to s we will get ys equal to theta, where yi equals to Ci1 xi1 plus Ci2 xi2 plus dot dot Ciri xiri. So from here we get that y1 plus y2 plus dot dot ys equals theta. Now the eigenvalues are mu1 mu2 dot dot mus, and they are all distinct, and their corresponding subspaces were y1 w1 w2 ws, right? According we have taken like this, that is mu1 mu2 dot dot mus. These are our distinct eigenvalues and their corresponding subspaces are w1 w2 dot dot ws. Now consider what does it y1. Y1 means this one, that is the linear combination of the vectors xi1 xi2 dot dot xir. And what is that xi1 xi2? We have chosen this xi1 xi2 all as basis of wi. That means these are all basis elements of wi. Now the linear combination of the basis element, that means all of this yi will belongs to wi. All this yi belongs to wi because yi is nothing but just the linear combination of the basis element of wi. So it will always belongs to wi. Now as because wi is a corresponding subspace, then we are considering this relation, that is y1 plus y2 plus dot dot ys. Then necessarily this y1 and y2 dot dot ys are linearly independent. If they are non-null, because they are all belongs to the basis element. So from here we can write y1 y2 dot dot ys are all linearly independent if they are non-null. If they are null element, that means theta, then there is nothing to say. Theta plus theta s times equals to theta. But if they are non-null, then they should be linearly independent because they are the linear combination of the basis elements. But here we are getting that y1 y2 dot dot ys equals theta. So it follows from this relation, this one, that is they must be equals to theta. That is y1 y2 dot dot ys are necessarily null vectors. Because if you check the relation y1 y2 plus dot dot ys equals theta, what are the coefficients here? Coefficients are 1, that is 1 into y1 plus 1 into y2 plus dot dot 1 into ys equals theta. That means all of these y1 y2 ys becomes linearly dependent as we are getting non-zero coefficients for them. So this becomes linearly dependent, but this cannot be possible. This is possible only when they are all theta. So y1 y2 ys are necessarily the null vector, that means theta. So what is y1 y2? This means ci1 xi1 plus ci2 xi2. So from here we can write ci1 xi1 plus ci2 xi2 plus dot dot ciri xiri equals theta, where I runs from 1 to dot dot s. Now again xi1 xi2 dot dot xir, what are the vectors? These form a basis for wi. This form a basis for wi. Now whenever they are basis element, they always should be linearly independent. That means all of these vectors, these are linearly independent, and we get this relation. That means all the coefficients should be 0 because this is the condition of being linearly independent. So all the coefficients ci1, ci2 and so on, ciri should be equal to 0. That means we have started with this summation cij xij equals theta, and we get these coefficients are equal to 0. That means from there we can write that xij, this set is linearly independent, right? And what are the numbers of this set? These are, and r1 plus r2 plus dot dot rs, because they are total xi1 xi2 and so on dot dot xri. That means they are total in number r1 r2 dot dot rs, which is equals to n. That means they will form a basis for v and k. K is the required field here, because we know that whenever a dimension of a vector space is n and we get n linearly independent vectors, they will form a basis for that vector space. So here we get total linearly independent vectors xij, and we have checked they are n in number total. That means they will form a basis for the given vector space v and k. So hence we can say that A is similar to a diagonal matrix. Okay, that means from this theory we can claim that A is diagonalizable if and only if its algebraic for each of the eigenvalues, algebraic multiplicity and geometric multiplicity should be same. Now we will solve one example, that is the application of this theorem. So write down example. Show that the following matrix is not diagonalizable. This matrix 2 8 0 2. I have taken a short example of 2 by 2 matrices. Then the calculation will be easier. So we have to prove this is not diagonalizable. That means there exists some eigenvalue or some characteristic value for which am not equal to gm. We just need to prove that, right? So let's start finding the characteristic value of this matrix. So considering a minus xi equals 0, we will get 2 minus x, 8, 0, 2 minus x. That is 2 minus x, its whole square equal to 0. So x equals 2 comma 2. So for lambda equal to 2, what is it algebraic multiplicity? Algebraic multiplicity means how many times does it occur in the characteristic polynomial. So this 2 occurs 2 times. So its algebraic multiplicity is 2. We need to check its geometric multiplicity is 2 or not. If it is 2, then it is diagonalizable, and if not, then it is not diagonalizable, the matrix. So for finding its geometric multiplicity, at first we need to find its corresponding characteristic subspace. For that reason we are writing ax equals lambda x. Then exactly the same procedure, just like the previous examples. xy, 2xy. So 2x plus 8y equals 2x. Then 0x plus 2y equals 2y. So this will give nothing, 2y equal to 2y. We just need to check this one. From this we can write 2x will be cancelled out. That is 8y equals 0, which implies y equals 0. So x, the characteristic vector, is denoted by xy. It will become x comma 0. That is x into 1 comma 0. Now check, this is a singleton set. This single vector, this should be always linearly independent, and this is spanning the characteristic subspace corresponding to lambda equal to 2. So if we take the characteristic subspace of lambda equal to 2 is suppose W1, then this singleton set 1 comma 0, this will form a basis for W1 because it is linearly independent and it is clearly spanning the space W1. So form a basis of W1. Then what is the dimension of W1? Only one vector contains in the basis, so dimension of W1 is equals to 2. That means geometric multiplicity of lambda is equals to 1, right? But the algebraic multiplicity, what we have computed earlier, what was the algebraic multiplicity of lambda? It was 2, which are not clearly same. So according to the previous theorem, we can say that A is not diagonalizable. Okay. So this is how we check a matrix or a linear operator is diagonalizable or not. Okay, these are the few examples you need to practice.